Hello everyone and welcome to part 3 of Astronomer reacts to the Flat Earth as alternative to gravity, also known as Incoherent Electrostatic Acceleration. Now, before we start, just two things. First of all, I've listened back to the full audio of the last episode and I noticed that my keyboard is pretty loud in that one, so I will use the mouse instead from now on. And the other thing is that the audio was rather weird. Testing different microphone placements, and I hope this one is better now. And also, my last video, part 2 of this one, has received almost 10 times as much views as my usual stuff. So thank you very much, whoever you are watching. I really do appreciate it. And let's continue. We were stuck at 7:37, and let's see what's going on this episode, shall we?
Curved, all the matter will follow these field lines as well. In this demonstration, instead of using a flat plane, I use two circular objects as my Gaussian surfaces. You can see that as the water settles after being sloshed around by me turning the wheel on the Van de Graaff generator, it comes to rest with a curve in the surface following the electric field lines between the two spheres.
As I mentioned last time, water reacts to electrostatic fields rather nicely. You can do that with a comb and with the water that comes out of your faucet. It's a really nice, small, little experiment that doesn't take much time. So I'm a little surprised that the water here reacts. I'm just wondering what he's trying to show here.
This is why the ionosphere.
Because I mean, yeah, no, let's go on.
A phenomenon that has never been created in a lab is a...
Yeah, let's recreate the atmospheric conditions of a planet in a lab. Sure, because that's possible, because you have a lab that's as big as a planet. Sure. Hey, one of my professors at university, I had in nuclear physics, right? Which is what I'm specializing in physics, as far as it looks now. When we talked about nuclear weapons, he of course said, well, he's very much against nuclear weapons. Such destruction is completely unwarranted, and the whole planet's in danger, and things like that. But he also said that in the far future, right, if mankind ever was to colonize hundreds or even thousands of planets, he says that should he still live to witness that, he will ask for a planet just to test nuclear weapons on. That statement reminds me very much of that. How exactly would you go about reproducing the whole ionosphere? You will need a whole planet for that. Because, right, the thing that, of course, he wants to say with that is that, oh, we don't know if there's an ionosphere because it hasn't been redone yet. First of all, you don't need to redo everything. Some things are just fine by measuring them, right? We can say, well, let's say when you measure the voltage from your some electric appliance in your house, right? You don't need to recreate the whole object to see if the voltage value holds. You can just measure it. The same holds for the ionosphere, right? Also, we have very sophisticated models, both in computers and on smaller scales, that tell us pretty much everything we need to know about the ionosphere. And also, like, we know how it reacts to radio waves, right? Because you can bounce radio wave off of the ionosphere, for example. I have done aerosol physics and atmospheric physics in university, and we learned a bit about the ionosphere there, and it didn't seem as if we had no clue about it, you know. But that's typical flat Earth talk. Oh, we haven't redone it, so it's fake. Which I love. The most scrupulous thing you could say is we haven't redone it, so we don't know, right? But even that doesn't really hold up, you know. You can just measure things. You don't need to redo everything.
A theory yet to be verified, but is needed to create this phenomenon here on Earth.
I'm unsure what he talks about. Oh, I mean, I believe he means that he requires an ionosphere for his model. In that case, yes, I will give you the ionosphere. You can have it. We have measured it. There is definitely an ionosphere there.
Maxwell himself changed Ampere's law, which stated plainly that
Yes.
without matter, no electrostatic field can exist.
No. Where, to the best of my knowledge, within Ampere's circuit law, there is no, which is the one that's you can see here, right? Ampere, really quickly. Ampere's circuit law essentially just says, well, you have this is a constant, right? This is one of the natural constants. I keep forgetting which. There's the dielectric constant, and then there's the electric field constant. I get those two mixed up by all the time, but there's the epsilon zero and the mu zero, which are two constants. Then here you have the charge density. Oh, I believe that's where he's running against it. He thinks it's normal density. No, this is the total density, or the total current density, which essentially just says how much ampere by, I believe, square meters you have. Electrodynamics is quite some time ago, and as I said multiple times before, I'm doing this blind, right? But I believe that J is in ampere per square meters. And what Maxwell has added is this part right here, which is called the displacement something current, probably. Does it say anywhere here? He has added that part here. I believe it's called displacement current. And the thing about displacement current, okay, I'll just have him explain it, which will be wrong.
Maxwell changed it with no scientific evidence.
Maxwell changed it because he noticed an error. Imagine, because okay, what's going on with the displacement current? What's it there, right? As of all the other Maxwell's equations, it's a rather fundamental thing with electrodynamics, because such is the nature of the Maxwell's equations. You have, on the left-hand side, you have the divergence, which is essentially a differential operator. So we are differentiating something. This is calculus. If you don't have calculus left, that is not a problem. The message that I want to convey here is essentially that you know how it's a differential operator. We are differentiating against something. And by the way, I was wrong. I said divergence. Of course, I meant rotation. Rot or curl. I believe it's called curl in English. I have only had that in German, so I don't know. I believe it's called curl. It looks at the rotation of a vector field, right? Yes, it has to be rotation because we're having a cross product. So essentially what we're looking at is how rotated magnetic field is in that case, right? And if you know magnetic field that whose curl is bigger than zero, which this one will be, that's the left-hand side of the equation, is equal to some constant times the current density, right? So the how much amperes per square meter you have. And now Maxwell had a thought experiment, right? Imagine you have a single piece of wire, and you have that wire in a loop, right? But instead of connecting the two ends, you put a capacitor at the end. And then he thought about it, and while we know that for alternating current, capacitors do not block the line, for direct current they do block the line, right? And without that part at the end right here, if we ignore that, Ampere's law would predict that there would be no magnetic field, because there's no current, because we have a capacitor there, right? But what Maxwell did is he added the necessary change of electric energy over time, right? So that he can account for that kind of thing. It was absolutely necessary. And when he says that there is no scientific evidence for it whatsoever, that tells me that he has never looked into electrodynamics, even on a very surface level. I remember we are being explained Maxwell's the Maxwell laws in in the second term of studying physics or astronomy for that matter, right? And it's kind of a really easy thing. The only thing that you need to get a hold of are these differential operators. There are divergence, there's the divergence, and then there's the curl, which are really easy. They are. I mean, oh no, gradient. So, oh god, I'm sorry. There's the gradient, there's the divergence, and then there's the curl. I'm getting confused with the German names here. And once you get a hold of these three and some basic vector calculus, which really isn't hard, some people even do it in school, you can get a hold of Maxwell's equations, at least in this form, rather easily, I'd say. So, I think it's funny. He clearly doesn't understand it. Very clearly. Also, Ampere's law, to the best of my knowledge, never states anywhere that there must be matter, although this is a note from me, there must be, because all charge-carrying particles we know so far also have a mass, and I believe that's necessary. I believe they have to have a mass for some particle physics reason, but I'm not good in particle physics, so let's not talk about that. But what he just said is plainly wrong.
Allowing it to gather magically above our heads in free space.
It's not magically.
Density and electric...
It's a change of the electric energy or the electric field over time that can also induce magnetism. Had he ever looked at a generator, he would know that. But then again, it's not a strong suit of flat earthers to do their own research, as they say.
Potential go hand in hand.
What did you say? Sorry.
Density and electric potential go...
Well, not density. We have charge density. The density of some things that are charged, right? That's an important thing. You can have absolutely neutral matter that is very dense. Like, I don't know, you can for example, if you have a cube of some very, very light metal, let's say aluminium, right? And then you have a cube of, let's say you have wax. Wax might be more dense than aluminium. I don't know. Imagine that you have something that's like wax. The wax thing won't hold charges as nicely as the aluminium cube. So it's not density, it's electron density, charge carrying density. And really what that boils down to when we talk about materials is we need to talk about solid state physics, which is a whole other kind of worms that I'm not opening right here. Not only because I'm not really good at it, but also because this would go way beyond what we're trying to do here. But this diagram I agree with. The charge density is essentially derived from some density of charged particles or ions or what have you, and this goes hand in hand with electric potential, because the more you have, the more electric potential you have, right? But there.
Go hand in hand. The denser something is, the more electric potential it can hold.
No. It needs to be that's not the only thing. The physics behind the conduction of electricity, which is necessary to hold charges, right? That is rather complex, and as I mentioned right before that, is a topic of solid state physics, which is complicated. But you can't just say the more dense things hold charges better. Then how come we continue to use copper and like aluminium for a whole bunch of applications and not use like lead for everything, apart from the fact that it's poisonous? But that's just plainly wrong. There are a whole bunch of things into that. You need to take into account the crystal lattice structure. You need to take into account the how freely the electrons can move through the material in solid state physics. This also then comes into chemistry and things like that. So you can't say that as a blanket statement.
Not that I believe in the model of the atom.
Very much not surprised. I love it when they selectively choose parts of kind of established science. like the Maxwell equation. Although he kind of tried to denounce the contribution of the Maxwell equations, or like of Maxwell to the Ampere's law, which then again I guess fits him. But I love how they put on with Ampere's law, but no atoms don't exist, which is like, well, choose one, maybe. Either you go completely against science or completely for science, but those strange in-between things, yeah.
But even the periodic table has a distinction on the amount of electric potential there is in the different elements. In this demonstration,
Does it?
I have a metal button hanging from helium balloons that keep the button buoyant.
A button? But what does he mean, a button?
Just above the ground. By only adding
Like
more
a button for a piece of clothing.
electrostatic potential to the button, you can see it will appear heavier and force the buoyant object
Electrostatic potential doesn't make things heavier. If anything, it makes it charged.
down along the
Although technically, if you make it a lot more negative, you have more electrons in there, which will make it heavier, but by a factor that's so little that you won't notice it.
vector lines created by the electrostatic potential difference. Without changing the density of the medium or the object, one can change the overall weight or gravitas of
Well, you don't change the weight. What you do here is you change the charge, and depending on how the other things around you are charged, this can cause a movement through the electromagnetic force, right?
the object.
Don't know what he's trying to show here. Essentially, if you do it, like the thing that he's essentially showing here is, yeah, electrostatic forces are a thing. Well, don't say, Sherlock.
To do an actual experiment on the topic of gravitation, this variable of electrostatic acceleration must be taken into account.
Yeah, Earth is roughly negatively charged, although very weakly so, as I mentioned previously. But that experiment might be valid, I guess. You can't really see it, right? Because you don't see what's going up in the balloons. If a normal person in a debate with a flat earther were to bring this up, right? The flat earthers would immediately scream, "Oh, you can't see the balloons, it's fake," right? So just mention
At all times. Now we will take a look at how different electric potentials of gases act in this electrostatic medium we live in.
And I believe we will save that for the next time, because we are already 17 minutes, almost 18 minutes in. I have, by the way, DFE, Destroying Flat Earth, or Destroy Flat Earth, or Debate Flat Earth, something like that, has recently brought out a video where he talks about some more of the incoherent electrostatic acceleration, which is a lot better than I could do, right? Because I'm doing this unscripted. I'm just looking at it and having a laugh. I highly encourage you to watch it. In fact, if I remember, I will put it in the video description. He has previously done a whole episode of things, although those were focused on the words. I sometimes I'm lost for words. He focused on Austin Witzit's video where he talks about incoherent electrostatic acceleration. I let me know if you want me to do some videos on the Witzit stuff, although I believe he's one of the more reacted to flat earthers, and I try to focus on a bit more of the outskirts of flat earth, if you will. Yeah, but with that, I thank you very much for watching. If you do watch it, maybe consider leaving a like or even subscribing. And I really do appreciate all of you people watching now. And with that, thank you very much for watching, and I'll see you in the next one.